People used to think of ocean currents as rivers in the sea, but they aren't like that at all. They're often associated with eddy systems. Satellite pictures show eddy fields at the surface. But currents and eddies occur beneath the surface too. To find out about the deep ocean circulation, we need to study water masses. Discovery 2 was one of several research vessels used for the pioneering study of water masses in the oceans. Much of this early work was done between the two world wars. At hundreds of stations throughout the oceans, they stopped to measure the temperature and salinity at various depths in the water column. They used the Nansen bottle and reversing thermometer, a classical standby of physical oceanographers. Deciding where to put the bottle on the wire, in other words, at what depth to collect water samples, must have been largely a matter of informed guesswork. As many as 30 bottles, each with a triggering messenger, were attached to the wire at intervals. When the bottles had reached the selected depths, the reversing and closing mechanism was triggered on each bottle in turn by a messenger weight sent down from the ship. The temperature of the deep water samples, recorded by the thermometers as they reversed, was read off with the help of a magnifier. Water samples were tapped off from the bottles after rinsing the flask to eliminate contamination, and they were used to measure salinity. The water samples had to be placed in a constant temperature bath because conductivity is temperature dependent, and salinity was measured using a conductivity bridge. The other important measurement made on the samples was the dissolved oxygen, using a standard titration method. All this laboratory work went on continuously, day after day, as the ship steamed from station to station. More than half a century on, oceanographers are still making the same measurements of temperature, salinity, and other properties. But scientists aboard the new Discovery and other ships now use more sophisticated instruments. Whole packages of measuring and sampling equipment can be simultaneously lowered into the sea. The data can be continuously monitored, analyzed, and stored on shipboard computers. One of the largest systematic water sampling programs of recent times was the Geochemical Ocean Sections Project, GeoSecs for short.
The principal problem in laying out a major scientific expedition program like the GeoSecs work is the location of the tracks and the stations that we want to follow in the time available. There are a lot of constraints. We want to sample the deep water in as many places in as much detail as we can. We're constrained by how far the ship can move in a certain length of time and by the areas that we actually want to work in. In the Atlantic Ocean, our problem was to study the deep water circulation with special emphasis on the deep flow in the western side of the ocean. Our first concern then was to lay a track out on the western side of the Atlantic, and you can see these tracks here, the various legs where they come in and out of the ports. These points on here mark the stations, where something like 58 different tracers are being measured at a series of 45 to 50 depths at each one of these points. Following this track down through here and across the circumpolar region, we were then able, in the time allotted, to put in a section up through the eastern side of the Atlantic and finally one across the mid-Atlantic ridge to get a section across the Atlantic Ocean. We hope to be able to provide a detailed description of the flow of the deep water, the rates that the deep water takes to move around the oceans, the times involved, the interchange with the surface waters, the buildup of pollutants in the deep water, and to provide really for the first time a detailed description of the entire movement of ocean water vertically, horizontally, and around the major basins of the world. Of course, this will take many years to accomplish, and many scientists will be studying these data for at least, say, 10, 20 years from now to be able to produce these detailed results. But ultimately, we hope to provide this detailed picture of the oceans that we have never had before.
Measurements must be taken in any sort of weather throughout the oceans to get a global picture of the water masses. So reliable and sophisticated equipment had to be developed. This rosette, designed specially for the project, contains 12 30-litre sampling bottles. base of the frame are 3 probes, which continuously measure salinity, temperature, and dissolved oxygen, and transmit that information back to the ship. Above the probe is an acoustic pinger, which measures the height of the package above the seabed, and at each end of the bottles is a lid, which can be electrically triggered to close. The rosette is clamped to the wire, and an electrical connection is made and tested. There are 2 rosettes, each with 12 bottles, set one above the other on the wire. As the rosette descends, continuous profiling of salinity, temperature, depth, dissolved oxygen, pH, and particulate matter is transmitted in coded form back to the ship through the wire. So the chief scientist has a constant picture of conditions at every point in the water column. The chief scientist on this leg is Wallace Brurker.
Here in the control center, the chief scientist has access to all of the geosex systems. We have a mini computer here. We have the readouts from the trawl and hydro winches. We have the communication with the bridge and with the winch. Over here we have the tape recorder that's recording the signal coming up from the underwater package. We have a real-time display here of depth, temperature, and so forth of the water that the package is going through. We have here display scopes that can show the plots of temperature versus depth, salinity versus depth, and so forth. In fact, right now, I'll type in one of the command to make this one of these plots.
These electronic displays mean that on the basis of what you see while going down, you can plan the sampling strategy to be followed while coming up. By pressing this red button, a large current pulse is sent down the wire to override the incoming signal and to close any one of the bottles on the rosettes, trapping 30 liters of water at a particular depth. The first measurement made on the return of the rosette is temperature from the reversing thermometers. This gives a calibration for the electronic depth and temperature sensors. Then water is drawn off from the Niskin bottles for analysis in the ship's laboratory. Here, salinity is being measured on a conductivity bridge. Like the reversing thermometer, this is the same technique which was used on Discovery 2. Salinity is one of several traces which tells us where the water comes from, and these are the traces which can be analyzed on board. An important source region tracer is dissolved oxygen, measured here by a standard titration method. Other source region tracers measured on geosex cruises were nutrients, measured on the autoanalyzer, and, of course, carbon. But the real advances made by geosex were with time tracers, which tell us how fast the water is moving. Because of the complex equipment required, radioactive isotopes such as carbon-14, strontium, tritium, and several isotopes of helium had to be measured in shore laboratories. The one exception was radon-232, with a half-life of only 4 days, so this had to be measured on board. When the analyses were completed, the data were punched onto computer cards, ready for transfer to permanent data storage. This magnetic disk carried all of the geosex Atlantic and Pacific data, plus other water mass information, including data from Discovery 2 and even the original Challenger expedition. All this information was stored at the Geosex Data Bank in California for access by computer link-up from anywhere in the world. Things haven't changed much since the time of geosex in the 1970s. The rosettes are still dominated by the sampling bottles and reversing thermometers, and the samples are analyzed in much the same way. But new equipment is being developed all the time. On top of this rosette is a laser beam instrument for measuring light transmission in the sea. Oceanographers have traditionally measured currents, Savonius rotors, used for centuries as wind pumps, now drive small generators whose electrical output signal is recorded on a cassette inside the cylinder, storing up to a year's worth of deep current data.
And we ought to draw vertical lines through those.
1973, Bermuda. A group of scientists headed by Henry Stommel meet to discuss the mid-ocean dynamics experiment, or MODE for short. Among them is Walter Monk.
The MODE expedition was the most ambitious undertaking of its kind. A certain volume of ocean was selected, 200 by 200 kilometers from top to bottom, and then the hell was instrumented out of this volume.
MODE was a combined British-American effort in which the latest in ocean technology was put to work, much of it for the very first time. But what were these instruments looking for? Putting it simply, they were looking for weather, not in the atmosphere, but in the deep ocean.
Until about 10 years ago, what we really did in oceanography, in studying currents, you might classify as climatology. It was attempting to give the average state, and by average we mean really a very long time average, like a 10-year average. And then one spoke basically of two types of circulations. The relatively shallow ocean circulation, which is driven by the wind, and the very deep circulation, which is the result of density currents associated with water masses formed usually at very high latitudes. This somewhat blissful picture of a simple and smooth average ocean circulation was interrupted about 10 years ago when John Swallow dropped his current floats from the ship Ares and found that they didn't behave at all as anyone expected. Instead of moving at a very slow, steady velocity in one direction, they moved much more rapidly in another direction. And moreover, another float, which was only 20 kilometers away, I think, and which was supposed to have done the same thing, decided to go in a quite different way. And everybody was aghast that the ocean should have these nonconformist, complicated features.
In the chart room aboard the Discovery, John Swallow talks about those early days and the ideas that led to the MODE project.
This idea at the time, you know, of getting another check on Henry Stommel's circulation model, where he was predicting that the deep water away from the boundary would move back towards the poles.
With a gentle sort of upwelling.
Yes, whereas all the southward motion in the deep water would be carried in the western boundary current. And whereas the traditional view was that you'd get a slow southward drift all the way across.
Like a lot of science, we start off looking for one thing and find another, completely unexpected. John Swallow's voyage was just like that. These floats are designed to sink slowly to a predetermined depth where they become weightless or neutrally buoyant. As the currents sweep them round, their paths are acoustically tracked from the ship. Hanging from the lower end and just dangling in the water is the ballast weight and explosive release. When the release is fired, the weight falls away and the float returns to the surface to be picked up by the ship. Off it goes and the experiment is underway. But Swallow floats weren't the only floats to take part in MODE. The Americans used their sound fixing and ranging floats, or SOFAR floats for short. SOFAR floats are designed to be heard hundreds of kilometers away, and to achieve this, they make use of the sound channel. They're much larger than the Swallow floats, and they can work continuously for many months. Their characteristic hoots are emitted by the two resonant pipes on either side of the main tube, a sound similar to that made by some whales. Like Swallow floats, SOFAR floats are neutrally buoyant. In the air, they weigh almost half a ton, but on the surface they weigh only a few kilograms, and as they sink, they eventually become weightless. Each float is tuned to a different frequency, and the distinctive hoots are received by hydrophones in the sound channel, which are linked to shore-based listening stations. The fix is calculated by measurements of the time delays in receiving the float's signal at different stations. So no ship's required to track these floats, and once in the water, they'll operate for months. Floats are one way of measuring deep currents, but the mode scientists also used another approach, deep-sea current meters. In this lab, meters are being given a final check before being attached to a mooring. The meters record the north-south and east-west components of currents, working in much the same way as an anemometer measures wind speed and direction in the atmosphere. The data are stored on magnetic cassettes. Once thoroughly prepared and checked, the meters are attached at anything from 500 to 1500 meter intervals on the mooring cable and paid out over the stern. The ship steams slowly forward and the mooring is strung out on the sea surface, the whole thing being kept buoyant by floats. For a typical mooring, something like 4 kilometers of chain and cable had to be laid out over the stern. The number of current meters varied from site to site, but a typical mode mooring contained 4 or 5, covering depths from 500 to 4,000 meters. The top of the mooring is capped by a flashing light and radio beacon to help in the recovery when the moorings eventually retrieved. The bottom of the mooring, over a ton of anchor, was the final bit to be paid out. With the anchor gone, the whole mooring is pulled slowly down, and everybody wondered whether they would ever see the equipment again. To see what happens as the anchor sinks, look at this diagram of the mode area. The depth scale is highly exaggerated. The heavy anchor and the glass floats work together to pull the mooring into a vertical line with the top beacon at about 500 meters below the surface. From their fixed position, the current meters record currents which move past them, and this is the so-called Eulerian approach to current analysis. On the other hand, SOFAR floats move along with the water, and this is the Lagrangian approach. Ship time is very expensive. The arduous task of laying out the vast number of instruments continued day and night. This is what Walter Monk meant when he said the hell was instrumented out of this area. New instruments are deployed alongside older, better tried techniques. But what picture does it all give us? This analysis of the data collected from the mode area over the whole period of the experiment revealed water movements that showed the birth of a deep ocean storm. We're looking at a contour map of the 10-degree isothermal surface, which lies about 1,000 meters below the sea surface. This surface of equal temperature isn't flat. It undulates between hills, where the isotherm is nearest to the sea surface, and valleys, where the isotherm goes to its deepest. Warm water is less dense than cold water, so in the dips, where warm water goes deeper, we have a low-pressure region. Under the hills, where there's less warm water above, we have a high-pressure region. These contours are like the familiar isobars on atmospheric weather charts, and the currents swirl round the high and low pressure regions, just like winds in the atmosphere. The only difference is in the time and space scales between the atmosphere and the ocean. The ocean moves much more slowly. As the weeks progress, the pattern of ocean weather slowly develops, in a way very similar to the development of atmospheric weather. But even though the ships had returned to port, technology was still at work. Peter Rines, another mode scientist, explains.
Now, after the moat experiment was finished, everyone had packed up and gone home. They left some SOFAR floats behind because they were heard from land and there was no need of anyone out there. And these SOFAR floats drifted wherever they wanted to. In fact, in this case, they had stagnated for some months, and all of a sudden they spun into life. It circulated in a very strong eddy-like motion with speeds greater than a knot, which is a very fast flow for this part of the ocean. And it gradually worked its way westward until it hit a very significant bit of topography, the Blake Escarpment, at which point it shot to the south, again at very high speeds.
What causes these eddies? There are probably a variety of mechanisms, and I don't know the answer. But one thing is clear. These eddies are not the bearings that are being rotated by the general climatic circulation. They are much more like the gears that put momentum into the general circulation. In this sense, they are quite a bit like storms, which are not driven by the general circulation of the atmosphere, but are known to put momentum into the general circulation. The discovery of this mesoscale circulation of eddies has presented the oceanographers with a very tough problem. One way out would be to produce the ocean equivalent of weather maps. But the job in the ocean is much harder than in the atmosphere because the ocean eddies are so much more compact, so much smaller than the equivalent storms in the atmosphere. But nonetheless, there may be ways, possibly by the use of satellite observations, to produce such ocean weather maps, but we're certainly many, many years away from it. If you give up on this, it would be like if the meteorologist had given up on weather, and if he was satisfied to provide a pilot taking off from an airport with 10-year averages of February winds. Surely that wouldn't be a very useful piece of information. So we're left with a great challenge and no very good idea of how to go about it.
That was the situation as Walter Monk saw it in 1977. Since then, satellite technology and ocean modeling techniques have advanced greatly. On this satellite image of the Gulf Stream, you can see evidence of eddy formation. The pale green blob in the lower right is a cold core eddy. Mathematical modeling with powerful computers is another way of studying the evolution of oceanic eddy systems. On this model of eddies near the surface, the light blobs represent cold core eddies, the dark blobs warm core eddies. An advantage of mathematical modeling is that it enables us to look below the surface, which satellite images can't do. The eddies at deeper levels are not so energetic, but they're still there. We've come a long way from the old idea of currents as rivers in the sea. Modeling will soon enable oceanographers to predict how these swirls and eddies develop. In other words, it'll soon be possible to forecast the weather inside the ocean as well as above it.